Juan and hello everyone. My name is Ting Mi, and today I'm going to introduce a paper named Weight Normalization, a symbol reparameterization to accelerate training of deep neural network, written by Tim Salliman and Diadarik Kima from OpenAI in 2016. So I will introduce a bit about the background of neural network. A neural network involves a sequence of linear transformation. In a layer, a neuron activation is computed using this formula. Um, taking the product between the input to the neuron and the transform matrix weight W, or often called the weight matrix, and then add to the bias. Then the break activation Y is plugged into the nonlinear function such as the ReLU function to compute the activation for the neuron. In neural network, learning happens in two passes, the forward pass and the backward pass. In the forward pass, at each hidden layer, we compute the activations for neurons in the layer. And the activation then pass to the next layer of the network. And we repetitively do that until we reach the last layer. And at the last layer, we use the outputs to compute the loss. The loss is the deviation between the actual label and the predicted output. Um, so, and after compute the loss, we back propagate to compute the gradient of the loss with respect to the weight. And then we use the computed gradient to update the weight by subtract the gradient from the product between the grade, subtract the weight from the product between the gradient and the learning rate. However, this one problem happened in learning in deep neural network, which is the exploding and vanishing gradient. So in deep neural networks, such as convolutional neural network, um, involves hundreds and thousands layers. Since the activation propagate from one layer to the next layer to a deeper layer, the scale of the activation can change. It can increases as it goes to the deeper layer, or it can decreases as it goes to the next deeper layer. And um, and with that, when the scale decrease, that can lead to no variation in the neuron output. So the gradient is basically just zero. No learning happen, or in the case when the scale of the activation increase, there may be too much variation in the output. The gradient is very big, and that is called the exploding gradient, and that is not good for learning too. So the solution is simple. We keep the scale fixed at every layer as we propagate through the network. So in the past, researchers and people in the industry has used and also demonstrated the effectiveness of a method called batch normalization to keep the scale of the activation constant or fixed, stay fixed as it propagates through the network. So procedure is that for values of x over a mini batch, because when training we train with a mini batch. So when we compute the activation for neurons in a layer, we using y equals to x multiplied by the weight matrix plus the bias, and then plug in into a nonlinear function. We we also need an extra step, which is normalize or rescale our activation. So by first we taking the mean across the mini batch, and then taking the standard deviation of x over across the mini batch, and then we subtract the activation from the mean and then divide by the standard deviation. So the activation that we get at the end will be in a normal distribution with mean 0 and standard deviation 1. So we are able to keep the scale of the activation fixed. Though this can solve the vanishing gradients and these blowing gradients allow learning to happen, it can add some a side effect. So it add the noise to the procedure because now the prediction of an image is affected by other images that randomly selected in the mini batch. Though in some applications such as classification, adding noise can add regularization effect that help prevent the model from overfitting. Overfitting is the accuracy of the training larger than the accuracy of the testing data, the testing accuracy. So adding noise can help the model have better generalization. But in some application, adding regular adding noise can worsen the model, such as in deep reinforcement learning. Adding noise can destabilize the training, or in generative modeling, where we still suffer from underfitting rather than overfitting. So, adding regularization effect may be unnecessary and also may hurt the performance of the model. So, in this paper, the author proposed another approach that can solve that side effect.
The new approach is called weight normalization. Um, so the purpose of this is to solve the vanishing and exploding gradients, just like the batch normalization, but without adding the noise to the neural network. Um, so the proposal contains two parts. The first part is the initialization part. So we initialize the parameters as in batch normalization to get good scale at the start. And the second part is the reparameterization. We reparameterize the network to keep the scale during training. For the initialization part, um, so when we start with a neural network, we start with random initialization of weight and bias. And the initialization part of weight and bias happen in the first forward pass when epoch equals to 1. So for the first layer, for every unit, we just at normal, we compute the reactivation using the linear transformation W multiplied X plus B, and then across the batch, we compute the means and the standard deviation for that unit, uh, and use the mean and standard deviation to rescale the weight and the bias. For the weight, divide the weight by the standard deviation, and for the bias, we subtract it from the mean and divide by the standard deviation. And then we recompute the reactivation, use it and plug it into the nonlinear function. Uh, the effect is that we obtain the activation in normal mean 0, standard deviation of 1. So we effectively keep the scale of the activation, um, and then we pass it to the next layer, and so we're doing the same thing for every subsequent layer. At the end, we have all the weights are initialized in such a way that all the activation in each layer keep the same scale. And the second part of the proposal is called reparameterization. Reparameterization means the weight are reparameterized into a function of different parameters. Um, and so the weight can be written as the product of G and V divided by the Euclidean norm. So G is a scalar parameter that we has to learn. V is a vector of parameters. Also, we need to train this. And the V has the same dimension as the original weight vector. The denominator Euclidean norm is the square root of the sum of the square of element in the vector V. So during training, instead of taking the gradient of the loss with respect to the weight and update the weight, we take the gradient of the loss with respect to the G and the vector V. So they demonstrate mathematically that this will keep the scaling of the activation that we construct in the initialization part. The second benefit is that as we take the derivative, the gradient of the loss with respect to the V, in front of the formula is a scaling factor, G divided by the Euclidean norm, and this play a role as a learning rate. And they also said because V will grow during optimization, this scalar will goes down, so it basically is an automatic tuning of the learning rate. So in training neural network, we often has to know the learning rate, pick the right learning rate as we training over and over more epochs, and we often has to like um, effectively scale down the learning rate. But in this case, we have an automatic tuning of learning rates in place as we apply this method of weight normalization. So they to demonstrate that this will work effectively for different kind of application because this approach does not adding noise to the model. They demonstrate it in three different applications: the supervised classification, the generative modeling, and the reinforcement learning. So in the first experiment, you it is a image classification problem using cipher-10 dataset with no data augmentation, and they experiment with different approach, um, like the mean only batch normalization, the weight normalization, the normalization parameterization, the batch normalization, and so on. And for each model, they optimize the learning rate to give the smallest training error. So um, as you can see, the best result that they get is the combination of the weight normalization and mean only batch normalization. So the mean only batch normalization, adding the noise or the regularization effect to the model. um, Mean only batch normalization is good, but not a full batch normalization. Adding enough noise to the model is good, and also the model also getting the benefit from the weight normalization, allowing prevent from the model from the vanishing gradient and the exploding gradient, allowing effective learning rate. In the other experiment, they also see the better performance when they change from normal parameterization into weight normalization, in two experiment. One experiment with generative modeling with convolutional VAE, and one experiment with reinforcement learning. About the strength and the limitation of the paper, I believe this is a good paper with a lot of strengths. Um, so the first strength I see is it has good problem statement. So there is existing approach for the vanishing and exploding gradient, which is the batch normalization. However, uh, we they want to find a solution for the vanishing and exploding gradient without adding the dependency of the symbol into the MIDI batch, so that it can be a default choice for any neural network architecture, so it can work for every neural network architecture without adding the noise to the network. And they also did a thorough test on different applications to prove the validity of their proposal on the problem. Um, and this is the end of the presentation. Thank you very much for